some of you in Cologne. Who went to Cologne? So I was the only one that, well, you were in Cologne, I was in Cologne as well. So yeah, well, welcome to the second lecture. I want to start off just by sort of revisiting something that we discussed last time. And that is, well, I just want to quickly something. And that is this whole notion of dipole moment. Now, this is actually a very important concept, and I think, last week I just sort of glossed over it, and I want us just to look at this again. All right, so a molecule has a dipole moment essentially if it reacts to an electric field, right? So here, for example, we have some molecules that are polar, so there's a positive and a negative end, and you can see that it reacts to to an electric field once it's switched on. So there's a negative edge that attracts the positive poles, and this is the positive end that attracts the negative poles. Now, how does this actually work, right? We have to think about it in terms of vector algebra. Now here we have some molecules, dichloromethane, water, ammonia. You can see that we measure the dipole moment in units called debye. Incidentally, debye is a scientist from this region in the Netherlands. Debye. So you can see dichloromethane 1.87, 1.85 for water, 1.47 for ammonia. How do we figure out if a molecule is actually polar? Well, we first have to look at the actual bonds to see if the actual bonds in the molecule are polar or not. And how do we know how do we figure that out? Any suggestions? Electronegatiivity. So carbon and hydrogen have different electronegativities. That's why carbon is more electronegative than hydrogen. That's why I draw, this is a dipole moment arrow here. Same with hydrogen and carbon here, these are all the same. So carbon is more electronegative, that's why we have the arrow pointing towards the carbon. Chlorine is more electronegative than carbon, that's why the arrow is pointing that way. So this molecule has 4 polar bonds. Does everyone agree with that? Okay, there's 4 polar bonds. Now the next question is the molecule polar? Well, yes it is, but why? Because if you add these up here, you can think of these as vectors. And if you add up these vectors, you end up with a positive result. Yeah? So if you do a bit of vector analysis, you should have done a bit of vector analysis in mathematics in high school. Who's done some vector analysis? Okay. So think of these as vectors, dipole vectors, and if you add the vectors up and you get a positive result, the molecule is polar. Same here with water. Oxygen, hydrogen. Oxygen is more electronegative than hydrogen, that's why the arrow is pointing that way. Okay? And the same with ammonia. There, there, and there. So if we take water, let's think about water. We can think of water being pretty flat. Okay? Oxygen is more electronegative than hydrogen. So these are the dipole vectors. And if I add those two up, what's the result? Which direction will the dipole vector be pointing in? More or less up. You see that? If you add one after the other, the 2 vectors, you get a result that's positive. So this is a dipole moment. We call it a dipole moment that's pointing upwards. We'll practice this a little bit today in this tutorial. So what's important here is actually identifying, again, the molecular shape correctly, because if you don't have the right molecular shape, you can't actually get the vectors pointing in the right direction, and then you can't figure out if the molecule's polar. Let's do one more example. Methane. All right, first question. Are those bonds polar? The carbon-hydrogen bonds, are they polar? How do we figure that out? The difference in electronegativity. Which is more electronegative, carbon or hydrogen? Carbon. right? Carbon is more electronegative. So, how are we going to draw the dipole vectors? We're going to draw them like this, towards the carbon atom. Okay. Now, if we add, so the fact is this molecule contains 4 polar bonds. That's a fact. Is the molecule overall polar? Yes or no? What do you guys think? Any suggestions? Hmm?
Yes.
Yes, no, I mean, maybe. The answer is it's non-polar. It's non-polar because although the molecule contains polar bonds, if you add those up, you get a net result that is 0. Why? Let's try and build it. Let's pretend that these pens are the dipole moments of each carbon-hydrogen bond, right? So there's one pointing like this. So you all agree with me that they're sort of pointing like this, yeah? Agree? And then there's one pointing up. Now if we add these up, or sorry, there's one pointing down. So there's three pointing up, right? And one pointing down. Agree? Now let's do vector algebra. How do we do vector algebra? Well, we treat each of these as a vector. How do we add vectors? A vector is something you should have done in high school. It's something that has magnitude and direction. Alright, but the name, it's just the name. It's just the name. Let's just think about it in a more logical sense. Alright, so we've got these 3 polar bonds pointing like that and one pointing down. Alright, that's the situation for methane. Agreed? Agreed? Everyone agree? Alright. Now let's see what happens if we sort of add them one after the other. So here's one, here's another. I'm going to try and do this. Here's another. So you see what I'm doing? I'm adding one after the other. I'm just adding them head to tail. And remember I had one pointing down. So if I now take this one pointing down from the tip of this blue, where are we going to end up? We're going to end up back here again. So if you add them up, one after the other, the net result is 0. So the molecule, it's possible for molecules to have polar bonds, but as a whole, be non-polar. What about ammonia? That has a dipole moment. Why? It's very similar to methane, but what's the difference?
The loner.
Exactly. We don't have an atom sitting here to equalize these vectors at the bottom here, these vectors. So yeah. And this is now the last step in the whole process. So the first step is drawing the Lewis structure. The next step is identifying the molecular geometry, and then finally figuring out if the molecule is polar or not. So this is I think, quite important. Now, carbon tetrachloride is also non-polar. Now let's move on. And what I want to discuss today, what is the business of today's lecture, is chemical reactions and molar calculations. Now, I think most of you have encountered chemical reactions in some form or another, and you get different types of chemical reactions, obviously. Redox reactions are reactions involving transfer of electrons. We will discuss that right at the end of the course. You have acid-base reactions, okay? You have substitution, addition, elimination reactions. This is something one will typically discuss in organic chemistry. If you continue with a follow-on course in organic chemistry, you would discuss those sorts of reactions. Polymerization, how we make, for example, polyethylene, right? That's an important reaction. And ligand substitution reactions, these are reactions that we typically have in inorganic chemistry. Something, again, we'll discuss in the 2000 level course. So these are just some examples. There's really many, many different types of chemical reactions. The point is, the language of chemistry is writing it down in the form of a chemical reaction, okay? And there are certain steps involved here. I mean, most of you have certainly done this in high school, but the important thing is, of course, figuring out what formulae are associated, chemical formulae, with a process that you're studying. For example, if we have the combustion of ethanol, that's the formula for ethanol over there. If we react this with oxygen, right, we get carbon dioxide and water as products. Now, what we've done is we've taken a process and we've translated it into the language of chemistry, which is chemical formulae. The thing is, we have to balance these reactions because, I mean, atoms aren't just created out of nothing, right? It has to be balanced. What we have on the left, we have to have on the right. And typically how we balance these reactions is by inspection. What does that mean? By inspection. Means that we look at the reaction and sort of just figure it out how we balance it. Figuring out, for example, by counting what we have on the left and what we have on the right, seeing what we need on the left and on the right, and putting in the appropriate coefficients. So we call these stoichiometric coefficients. And if you count up the atoms on the left and the atoms on the right, you'll see that it exactly balances. So here we've got, let's count the carbons on the left. We've got 2 carbons here. On the right, we've got 2 carbons. So you see, introducing that 2 over there resulted in the carbons being balanced. Hydrogen, we've got on the left, we have a total of 6. 5 plus 1 is 6. That's the formula for ethanol. And on the right, we have 3 times 2 is 6. So introducing the stoichiometric coefficient 3 here has resulted in the hydrogens being balanced. Oxygen, how many oxygens on the left? 7. 3 times 2 is 6, plus 1 is 7. How many on the right? 2 times 2 is 4, plus 3 is 7. So it's balanced. And we call this balancing by inspection, meaning you look at the equation and figure out what do we need on the left and what do we need on the right. It's a little bit of a game, really. And we have other techniques to balance equations, which we're going to look at later. For example, with redox reactions, we have a special way of balancing them because it gets very difficult sometimes to balance by inspection, more complicated reactions. But balancing just by looking at it, and you've got to really practice this, is one way of doing it. Okay, so let's just sort of look at this again. What are we doing? We're taking a chemical process and we're translating it into the language of chemistry, which is formulae. And the second step is balancing by either inspection or using some more sophisticated technique. Right. The third step is always indicating the states of matter. Now, generally, one assumes that this is the states of matter at room temperature. Yeah? So at room temperature, ethanol is a liquid, oxygen is a gas, carbon dioxide is a gas. So these are basically next to each reagent or product. In brackets, you must always indicate the state of the thing, right? Just gives you more information. And finally, this is not always the case, but sometimes it's useful to give the reaction conditions. For example, if you heat something, you would use a delta, a capital delta, or you could write in the solvent, or the pressure and stuff like that. And you typically do that by the arrow. But if you're not given these conditions, then of course you don't have to write anything. So does everyone follow? Okay, I suppose this is quite boring for some of you, right? Okay, that's pretty much high school stuff, a revision. Okay, so again, the important issue here is stoichiometry, meaning getting the number of atoms on the left equal to the number of atoms on the right. And what does this actually mean? What this means is 2 possible interpretations. The first interpretation is 1 molecule of ethanol reacts with 3 molecules of oxygen to form 2 molecules of carbon dioxide and 3 molecules of water. That's what these numbers here mean. They're called stoichiometric coefficients. Another interpretation is 1 mole of carbon dioxide reacts with 3 moles of oxygen to form 2 moles of carbon dioxide and 3 moles of water. What is a mole? Yes.
It's the energy of the atom?
No.
atoms or molecules, right?
No.
No?
Okay, let's quickly just have a look at what a mole is, right? Because I think before we proceed, we should look at that. What is a mole? A mole is not something that runs around in the ground, right? That's an animal. There happens to be an animal called a mole that digs tunnels. It's not the same mole as in chemistry. So what is a mole? A mole is the amount of a substance. And it is the unit we use in chemistry. We don't use grams, we use moles. Why? We will see in a minute. How do we calculate the number of moles? There's a simple formula. It's the mass in grams of a substance. Grams of a substance divided by what? Divided by what? The molecular weight, or the molar mass. Now, the units, mass in grams is obviously grams. The units of molar mass is grams per mole. And so the units are moles. Now, what is molar mass? So we're really going back to basics here now. You should have done this in high school, but anyway, let's quickly spend some time on this. What is molar mass? What is the molar mass of water, H2O? 18. We go to the periodic table. Just a moment, let's have a look at this. Here's the periodic table. These numbers here at the bottom is the atomic weights or atomic masses or relative atomic masses. There's all sorts of different names for it, right? And basically, the molecular mass of a molecule is basically the sum of all of these. So H2O has two hydrogens, so it's 1.007, 1.008, 2 times 1.008 is around 2, and oxygen is 15.999. So what's the molecular weight of water? 18, approximately. Right? It's 18 point something. You shouldn't round off to 18, you should include that point something, right? We now at university, so we're going to be accurate. So if I have 18 grams of water, how many moles of water do I have? Here's the formula. 1 mole. If I have 36 grams of water, how many moles of water do I have? 2. All right, what is the molecular weight of glucose? I think that's the formula. Yes. C6H12O6. What's the molecular weight? Or these are all equivalent terms. Some people call it molecular weight. Some people call it molar mass. Whatever. It's basically the mass of the molecule. So what is the molar mass of glucose? How do we calculate it? Well, yes, the molar mass of carbon, which is 12 well, let's look at the table. It's 12.011 grams per mole times 6, because there's 6 of them. Plus, yes, the molar mass of hydrogen is 1.008 grams per mole. Don't forget units. By the way, a note on that, always write down the units of something, always, and then cancel them at the end. Units, units, units. I cannot stress this enough. Times 6. Plus what? Oxygen is 15.999 grams per mole times 12. Sorry, I think this is C6H12O6. Okay, yeah, the formula, it's not the formula of glucose. The formula of glucose is actually C6H12O. C6H12O6. So sorry about that. But anyway, that's just some hypothetical organic compound. Let's call it that. And that is the molecular weight. That's how we calculate it. And you put that in your calculator and you sum it. And then if you have a certain mass in grams of that substance, you can calculate the number of moles. Any questions?
What do you divide by?
Divide by what?
By mass in grams, right?
You take the mass in grams divided by what we've calculated there. So can someone actually calculate that? Does someone have a calculator? Let's calculate that.
But the mass in grams would be given, right?
Yes, yes.
I would just divide it by.
So let's calculate this. This is not glucose. This is some organic compound. Some hypothetical compound. Right. What is the molecular weight of this compound? Any Circa is calculating it for us.
270.
200 and
70 point 102.
point
102.
102. All right. So that's the molecular weight, grams per mole. So if I have 3 grams of glucose, of 3 grams of the substance, how many moles do I have? 3 divided by that value, moles. All right, so that's how we calculate moles, and that's super important that you can do this, right? Because that's like really what it all boils down to in chemistry. We work in moles, we do not work in grams. Now let's just go back here for a moment to where we were. Okay. So, okay. So that's very important, and that's really what that sort of means there. It's 1 mole of ethanol reacts to 3 moles of oxygen to give 2 moles of carbon dioxide and 3 moles of water. All right. Now, another thing I want to just briefly discuss is the notion of solutions. Very often in chemistry, when we do reactions, it's convenient to make a solution of a substance because, you know, it's better to add a solution to another solution for a reaction to take place than just to throw 2 solids together, right? Stuff likes to be in solutions. And if we're working in solutions, we typically need to work with concentrations, molarity. Now, what is that all about? Now, concentration, there's different types of concentration. We have molar concentration, which is the most important. And really what it comes down to is the concentration is expressed in moles per liter or moles per decimeter cubed, right? So the formula is concentration is number of moles over volume. N is the number of moles, V is the volume in liters or decimeters cubed. A liter and a decimeter cubed is exactly the same, right? So you can say moles per liter or moles per decimeter cubed. It's the same thing, okay? So we talk about concentration. And the unit for concentration, or this as we're defining it here, is moles per decimeter cubed, or moles per liter, also written as moles per decimeter cubed. By the way, this is the preferable way of writing it in science, right? Use scientific notation, or moles per liter. Okay, so that's an important point, and that will crop up as well in calculations. Concentration. Now we talk about the molarity of a substance, which is essentially what the concentration is, okay? So if I take 3 moles of a substance and I dissolve it in a liter of water, then what's the concentration? So if I take 3 moles of a substance dissolved in 1 liter, what is the concentration? 3. The concentration is, sometimes you can write it like that. That's the square brackets is the concentration, is 3 moles per liter, or 3 moles per decimeter cubed. We call that the molarity. The molarity is 3. Molarity. And we write molarity shorthand. Chemists like shorthand with a big M. All right, so we've now got the tools. We've got moles, we've got molarity. To now actually do some real chemical calculations. Okay. One point that just occurred to me. You said earlier 6.02. What was she talking about? 6.02. What is
The
that?
number of everything.
Avogadro.
Okay.
Avogadro's constant. What's Avogadro's constant or Avogadro's number? Anyone want to venture a guess? Also important.
6.25 times minus 22.
6.02, Avogadro's number is 6.02 times 10 to the 23. It's a big number. You know what that number is? It's the number of particles in 1 mole of a substance. That's what it is. So how many water molecules are there in 18 grams of water? How many water molecules in 18 grams of water? How many moles of water are there in 18 grams of water? 1 mole. So how many water molecules are there in 18 grams of water? 6.02 times 10 to the 23. How many hydrogen atoms are there in 18 grams of water? How many hydrogen atoms? Times 2. Exactly. So this is an important thing. So that's why I write here number of particles. Because if I'm dealing with molecules, which I was just dealing with, 18 grams is 1 mole, there's that many water molecules in 1 mole of that substance. But each water molecule has 2 hydrogen atoms. So 1 mole of water molecules will in fact have 2 times this number of hydrogen atoms. It's a big number. And that's actually quite amazing, right? To think that in 1 drop of water there's so many 10 to the 23. 10 to the 23, that's really an enormous number. So that gives you some idea of how many particles there are. So what if we just looked at, let's revise. Molarity, Avogadro's number, moles, molar mass, all of these things are interrelated. Okay, you must be comfortable going from one to the other and interconverting between these different things. Okay, so we've now got the toolbox to actually do some chemistry. Right? These are just preliminaries. What we're going to discuss now is we're going to now look at chemical reactions, and a very important issue is the notion of a limiting reagent. Now, if I do a chemical reaction between two, if I take beaker A and beaker B and I throw them together, 2 substances to do a chemical reaction, and I'm not careful in weighing it out, it could be that there's more of the one reagent than the other, and that when the reaction's gone to completion, I've sort of run out of the one reagent and there's still, the other reagents are still left over, right? That's what a limiting reagent is all about. We've got to figure that out in order to do chemical reactions. Now, the analogy I introduce here is making hamburgers, so that you can understand this in a simple way. Let's suppose we're at a barbecue, okay? And I have only 2 hamburger patties, 2. That's not very much, but okay. I have 2 hamburger patties and I have 5 bread rolls, right? Buns, bread rolls, whatever you want to call them. Brötchen, Semmel, okay, if you're in southern Germany. Okay, so how many hamburgers can I make? How many hamburgers can I make? 2. Can I only make 2? Because I've only got 2 hamburger patties. So when I've made those 2 hamburgers, what's going to be left? 3 bread rolls are going to be left. Meaning that the bread rolls are in excess. The hamburger patties are the limiting reagents. I can only make as many hamburgers as there are hamburger patties. Okay. So I can only make 2 hamburger patties. Let's now suppose I make 2 hamburger patties. What would the yield be of the reaction? in German Ausbeute, what is the yield? 100%. If I make 2 hamburgers, I'm going to have bread rolls left over, but based on the limiting reagent, which is, or the limiting factor, which is the hamburger patties, I can, and if I successfully make 2 hamburgers, that means I've converted both of the hamburger patties to hamburgers. That's 100% yield, right? I'm going to have bread rolls left over, but that's, that's coincidental. The yield, Ausbeute, is 100% if I make 2. Now let's suppose, while I'm grilling the hamburgers, or the hamburger patties, I'm grilling them on the fire or whatever, one sort of falls into the fire and burns, and I only end up making 1 hamburger. What would the yield then be? 50%. Yes. 50%. So I start off with 2 hamburgers, but I only end up with 2 hamburger patties. I only end up with 1 hamburger. The yield, based on the limiting reagent, which is the hamburger patties, is 50%. Okay? What if I really mess up the barbecue and I only end up making half a hamburger? What would the yield then be? 25%. Okay, so I think this is a very valuable analogy in understanding limiting reagents. All right, and now, we've just sort of looked at this in terms of hamburgers, but when we're dealing with chemical reactions, one of the most important things is actually determining the yield of a reaction, okay? And basically, you sort of have a feeling of that now in terms of hamburgers, but now sort of translate that into chemistry, right? So it's basically the percentage yield, Ausbeute, I really like that word, Ausbeute, is the actual yield over theoretical yield, okay? And we're going to look at this in a moment. So we're going to do an example where we practice all of these things. All right, and this is what it all boils down to. All right, you must be able to apply what we've been discussing, right? You'll be confronted with a chemical reaction, and then you have to sort of do the calculation. So let's do this together. What do you say? Right, this is a typical problem. You're a scientist in a laboratory doing a chemical reaction, and you want to determine the yield, the percentage yield. How do we do that? Okay. So, here's a reaction. We're taking 6.27 grams of iron, elemental iron, and reacting it with 4.55 grams of iodine. Okay? We're making iron 3 iodine. That's the product. And then I'll tell you, at the end of the reaction, I actually isolate in real life, in a laboratory, 1.07 grams of iron iodide. What is the yield of the reaction? Now, there are many steps to this. The first step is converting this written story into chemical language. In other words, writing down a chemical reaction. So what is the chemical reaction here? Well, we're taking elemental iron, which is a solid at room temperature, and we're reacting it with iodine, which is what at room temperature? Solid, liquid, or gas? No? Solid. Probably it will involve some heating, that's why I'm putting the arrow there. And we form, the product is Fe, as it's written there, Fe3 iodine. Now what does that mean, Fe3 iodine? It's iron 3, the oxidation state plus 3. So the formula will be FeI3, right? Because each iodine is 1 minus, so if this is iron plus 3, in order to balance it, we need, of course, to have 3 iodine, three iodine atoms attached to it. Is everyone happy with that? I've translated the story here into a chemical equation. Is everyone happy so far? Yes?
It's not balanced.
Sorry?
It's not balanced.
It's not balanced. Step 2. So step 1 is translating the story into the language of chemistry, a chemical equation. Step 2 is balancing it. So how do we balance this? By inspection, how do we proceed? Any suggestions?
Shall we see that?
You can start.
Well, let's put a 2 here. If we put a 2 there, then I'm going to have to put a 2 here because then I've got 2 ions on the left. But if I do that, then I need to put a 3 here. Now it's balanced. And by the way, when you do this, when you play this game of balancing by inspection, you know, see that it's in its simplest form. In other words, if there's a common factor, you know, divide through by it. You know, get it into its simplest form. And I mean, there's no common factor here, so that's the simplest. So now it's balanced. We're making progress. Right, now what's the next step? The next step is to go from grams to what? Moles. Because we're not working grams in chemistry, we work in moles. And moles are not creatures that run under the ground. They are the units of chemistry. So we have 6.27. Now let's do this together. I see my notes have been... Where are my notes? I brought them in here, and I see they must have gone missing in this pile of tutorials. Yes. Okay. Now don't forget, we need to, this is a solid as well, by the way, so don't forget that. All right, so we're now going to work out the number of moles. How do we do that? Well, I've just said, to calculate moles, we take mass over molar mass. So you can write N, which is the symbol for moles, N of iron. How many grams do we have? 6.27 grams, divided by the molar mass of iron. What is the molar mass of iron? Any ideas? Well, you can't know this out of your head, but you can go to a periodic table, and we see there it's 55.85. Let's round it off to 2 decimal places. 55.85 grams per mole. The units cancel, and if we calculate that, we get 0.112 moles of iron. Does everyone follow? Now let's calculate the number of moles of iodine. We proceed in the same way. We have, according to our little story, we have 4.55 grams of iodine. What is the molecular weight of iodine? I2. How do we calculate that? We go to the periodic table, we look at the molecular weight of iodine multiplied by 2, because the molecular formula is not I, it's I2. And you get to a value, if you do that, you can check this, of 253.808 grams per mole. Units cancel, and we get 0.0179 moles of iodine. What's the next step? Remember the hamburger analogy.
You have to know which one is an excess.
Correct. And how do we figure that out? Now, this is the key step. This is the key step. What do we do?
You just pick one, for example, the first one, and then you calculate how much you need from the other one,
Correct.
and then you see.
Absolutely correct. Did everyone get that? You pick one of the two. Let's pick iron, right? Let's pick iron. You consider one of the reagents, and you calculate how much of the other one you need according to the balanced equation for it to be consumed, and you see if you have more or less of that substance. So let's see what happens. If I take the amount of iron that I have here, 0.112 moles, how many moles of iodine do I need to consume, according to the reaction, all of the iron? How do we calculate that? So the question is, from the perspective of iron, remember the hamburger analogy. From the perspective of iron, how much iodine is required to consume it? according to the balanced chemical equation. That's the question we're asking. And how do we calculate that? We use logic and common sense. We say, well, look, we've got 0.112 moles of iron. So I'm going to require 0.112. You see, I have very bad habits, and this is because of my background. Sometimes I use a comma and sometimes I use a point. Don't get confused. It's just because I grew up in South Africa and there we used points. And then I was in Germany for 9 years and we used commas, so I interchange between the two. You can choose either one, right? So sometimes I use a comma, sometimes I use a point. A point is better, incidentally. Alright, so the question is, how much iodine do I need to consume all of this? Well, we have 0.112 moles of iron, and we're going to multiply that by the stoichiometric ratio, 3/2. Does everyone follow this very important step? Yes. 2 moles of iron react to 3 moles of iodine. In order for all the iron to be consumed, I've got 0.112 moles. I'm going to require 3/2 moles of iodine. All right? And if 3/2 moles, if you calculate that, what 0.112 times 3/2, whoops, equals 0.0179 mole. That's how much iodine I need to consume all of the iron. Do I have that? Do I have that much iodine present, yes or no? Yes. In fact, no, sorry, there's a mistake here. Yeah, sorry. 0.112, sorry, this is 0.168 mole. Sorry about that. Yeah. So, let's do that again. In order for all the iron to be consumed, I require 0.112 moles times 3/2 is 0.168 moles of iodine is required. Do I have 0.168 moles of iodine? Yes or no? No, I have much less. Look at that. It's essentially an order of magnitude less. So what's the limiting reagent? The iodine. It means that from this point forward, we're going to consider only the iodine, because that's going to dictate the yield of iron 3 iodide. At the end of the reaction, there's going to be a lot of iron unreacted left over. Alright? Now, incidentally, you can also do this whole thing from the perspective of iodine. You can say, okay, let's consider from the perspective of iodine, right? How much iron do I need to consume all the iodine? And then you would say 0.0179 multiplied by what? 2/3. 2/3, because I'm looking from the perspective of iodine. And then you would see that you'd come to the same conclusion, basically. So it's very important to be able to figure this out. Okay, so now how do we proceed? We want the yield, right? We are told that we isolate 1.07 grams of iron 3 iodide at the end of the reaction. What is the yield? So let's go on. We now know that I2 is limiting. So therefore, what will be the theoretical molar yield? What is the theoretical molar yield of FeI3? That's a question. What is it? We figured out that iodine is limiting, so what is the maximum amount of iron iodide that I can get out of this reaction under these conditions? What is the maximum amount? Maximum. Theoretical. Well, I have 0.0179 moles of iodine available. We figured out that that's the limiting reagent. That's like the hamburger patties. So if I've got that much iodine present, how much iron iodine can I get maximum amount theoretically? 0.0179. See there, I'm using the comma again. Moles times what? Times 2 over 3. Times 2 over 3. You see the stoichiometric coefficients. And if you calculate that, you get 0.0119 moles. Is the theoretical yield. Does everyone follow that step? We've taken the limiting reagent, which we've established is iodine, and we've said, okay, this is the limiting reagent, this is the hamburger patties. I'm only going to get as many hamburgers out of this as I have iodine present. You see, think about that analogy. It's very useful. So I have got a total of 0.0179 moles of iodine. So the maximum amount of iron iodide is going to be this number of moles times 2 over 3. In other words, the stoichiometric ratio of iron iodide to the limiting reagent iodine. Does everyone follow that? Now I have the number of moles, with the maximum amount of moles of iron iodide that I can get, and what we now have to basically do to get, we're nearly at the end actually, of this calculation, is we've got to say, okay, I have 1 point, but I isolate 1.07 grams of iron iodide. So what do I do with that? I convert that to moles. We don't work in grams, we work in moles. So number of moles of iron iodide is 1.07 grams divided by, what is the molecular weight of iron iodide? How do we calculate that? It is, let's just do it like as a thought experiment. How do we calculate that? So molecular weight of iron plus 3 times the molecular weight of iodine, because the formula is FeI3. And if you do that, the molecular weight of iron iodide, that's how you write molecular weight of FeI3, is 436.557 grams per mole. So we plug that in here, 436.557 grams per mole. The units cancel and we end up with a value of 2.45 times 10 to the minus 3 mole. Now, how do I calculate the percentage yield of the reaction? What is percentage yield? Percentage yield is actual yield. It's actual yield over theoretical yield times 100. What is the actual yield? The actual yield we've just calculated is 2.45 times 10 to the minus 3 moles. The theoretical yield is essentially 1.19 times 10 to the minus 2 moles. So how do we calculate the percentage yield? We divide the two together and you get a value of 20.5%. That's the yield of the reaction. Now, just a couple of notes. It doesn't matter how you do this. Like here I've divided moles by moles. I calculated the theoretical yield here in terms of moles, and I calculated the actual yield in terms of moles. Moles cancel moles. Actual yield, you see that the units will cancel and you end up with a percentage. A yield is a dimensionless thing. It's a percentage. Alternatively, I could have converted, if I wanted to, this is important, I could have converted that to grams by multiplying by the molar weight of iron iodide, right? That would have given me the mass in grams of iron iodide, and then I could have simply divided that by 1.07. In fact, maybe let's do that. Can someone please yes? Same question? What is 0.0119 times 436.557? Can someone please calculate that? I just want to show you, you're going to arrive at the same answer if you work in terms of grams. All right? Please calculate that. So, I'm just converting this back to grams by multiplying by the molar weight of iron iodide. What is the value?
Wait, so it's 0.0119 multiplied
Sorry,
by...
0.1?
No, is it that multiplied by the 4?
By 4.
Yeah, okay.
Yes, that's 0.0119 times 436.557.
5.195.
Sorry?
5.195.
5.195 grams. That is the theoretical yield. Now I've just expressed it in grams. So you see, now I can calculate the percentage yield how? By simply dividing 1.07. What is 1.07 grams divided by that value? You arrive at the same percentage. You see, so you can either do it in terms of moles or in terms of grams. Now, yes?
Sorry, but why is that the actual yield? Because 1.07 was isolated, so that was at the end of the reaction when I got, right?
Yes, that's the actual yield.
Okay.
So it's 1 point. So that's what you physically isolate in real life. The theoretical yield is what we calculated here. In other words, the maximum amount. If you assume that there's 100% conversion from the perspective of a limiting reagent. So now I've written down here as a guide. You guys really need to practice this. This is of paramount importance. The steps. You can expect something like this in the midterm. Okay? Now, just before the break, the periodic table is your best friend. Don't forget that. These are the molecular weights at the bottom here. Very important. And because we're not at school anymore, we don't round things off. We use the accurate molar weight in or molecular relative atomic masses as they stand here. Okay. So hydrogen is not 1, it is 1.008. Oxygen is not 16, it's 15.9994. Okay? Yeah. Precision. Now, here is an example that I'm not going to go through, but I want you to do this as a homework exercise to practice. I will give you the solution, and you can see if you get the right answer. What is the yield if in reality 1.12 kilograms? Kilograms, remember kilograms. Moles are, how do we calculate moles? Mass in grams, not kilograms. Don't fall into the trap. What is the yield of the reaction? All right, here's a very nice example of how the synthesis of aspirin, right? This is the industrial preparation of aspirin from salicylic acid and acetic anhydride. So you can see this is very important what we're doing, right? And the question is, I'll give you the solution and you can try this at home. The yield, the value you should get to, the gram solution, so the percent yield, is 86.2% aspirin. That's what you should get to. So write that down and give this challenging question a go. This is a challenging question simply because, but you're proceeding exactly the same way because we're using more complex formulae here, but it's all the same. It's all the same. Don't ever get scared in chemistry, right? It's all the same. All right. So I propose we now take a 5-minute recess and reconvene in 5 minutes, and then we're going to continue with the next topic, which is catalysis. You all look very sheepish today. Yeah, like a little bit scared, kind of.